Part 1: The difficult birth of the science of elasticity, or the springiness of solids. Let us begin at the beginning with Newton, who said that action and reaction are equal and opposite. This means that every push must be matched and balanced by an equal and opposite push. It does not matter how the push arises. It may be a dead load, for instance, that is to say a stationary weight of some kind. If I weigh 200 pounds and stand on the floor, then the soles of my feet push downwards on the floor with a push or thrust of 200 pounds, that is the business of feet. At the same time the floor must push upwards on my feet with a thrust of 200 pounds, that is the business of floors. If the floor is rotten and cannot furnish a thrust of 200 pounds, then I shall fall through the floor. If, however, by some miracle, the floor produced a larger thrust than my feet have called upon it to produce, say 201 pounds, then the result would be still more surprising because, of course, I should become airborne. The New Science of Strong Materials, or Why You Don't Fall Through the Floor, Chapter 2. We might start by asking how it is that any inanimate solid, such as steel or stone or timber or plastic, is able to resist a mechanical force at all, or even to sustain its own weight. This is, essentially, the problem of why we don't fall through the floor, and the answer is by no means obvious. It lies at the root of the whole study of structures and is intellectually difficult. In the event, it proved too difficult for Galileo, and the credit for the achievement of any real understanding of the problem is due to that very cantankerous man Robert Hooke, 1635–1702. In the first place, Hooke realized that, if a material or a structure is to resist a load, it can only do so by pushing back at it with an equal and opposite force. If your feet push down on the floor must push up on your feet. If a cathedral pushes down on its foundations, the foundations must push up on the cathedral. This is implicit in Newton's third law of motion, which, it will be remembered, is about action and reaction being equal and opposite. In other words, a force cannot just get lost. Always, and whatever happens, every force must be balanced and reacted by another equal and opposite force at every point throughout a structure. This is true for any kind of structure, however small and simple or however large and complicated it may be. It is true, not only for floors and cathedrals, but also for bridges and aeroplanes and balloons and furniture and lions and tigers and cabbages and earthworms. Weight, such as an ordinary brick, from some support which might be the branch of a tree by means of a piece of string, Figure 1. The weight of the brick, like the weight of Newton's apple, is due to the effect of the Earth's gravitational field upon its mass, and it acts continually downwards. If the brick is not to fall, then it must be sustained in its position in mid-air by a continuing equal and opposite upwards force or pull in the string. If the string is too weak, so that it cannot produce an upward force equal to the weight of the brick, then the string will break and the brick will fall to the ground again like Newton's apple. Figure 1. The weight of the brick, acting downwards, must be supported by an equal and opposite upward pull or tension in the string. However, if our string is a strong one, so that we are able to hang not one, but two, bricks from it, then the string will now have to produce twice as much upward force, that is, enough to support both bricks. And so on, of course, for any other variations of the load. Moreover, the load does not have to be a dead weight such as a brick. Forces arising from any other cause, such as the pressure of the wind, must be resisted by the same sort of reaction. In the case of the brick which hangs from a tree, the load is supported by the tension in the string, in other words by a pull. In many structures, such as buildings, the load is carried in compression, that is by pushing. In both cases the general principles are the same. Thus if any structural system is to do its job, that is to say, if the load is supported in a satisfactory way so that nothing very much happens, then it must somehow manage to produce a push or a pull which is exactly equal and opposite to the force which is being applied to it. That is, it has to resist all the pushes and pulls which may happen to arrive upon its doorstep by pushing and pulling back at them by just the right amount. This is all very well, and it is generally fairly easy to see why a load pushes or pulls on a structure. The difficulty is to see why the structure should push or pull back at the load. As it happens, quite young children have had some inkling of the problem from time to time. Very often available, nor is it necessary. If the cat's tail had happened to be attached, not to the cat, but to something inert, like a wall, then the wall would have to be doing the pulling. Whether the resistance to the child's pull is generated actively by the cat or passively by the wall makes no difference to the child or to the tail. Figures 2 and 3. How then can an inert or passive thing like a wall or a string or, come to that, a bone or a steel girder or a cathedral produce the large reactive forces which are needed. Figure 2. Do stop pulling the cat's tail, darling. I'm not pulling, mummy, pussy's pulling. Figure 3. It doesn't make any difference whether pussy pulls or not. The power of any spring is in the same proportion with the tension asterisk thereof, that is, if one power stretch or bend it one space, 2 will bend it 2, 3 will bend it 3, and so forward. And this is the rule or law of nature, upon which all manner of restituent or springing motion doth proceed. Robert Hooke. By about 1676 Hooke saw clearly that, not only must solids resist weights or other mechanical loads by pushing back at them, but also that 1. Every kind of solid changes its shape by stretching or contracting itself when a mechanical force is applied to it. 2. It is this change of shape which enables the solid to do the pushing back. Thus, when we hang a brick from the end of a piece of string, the string gets longer, and it is just this stretching which enables the string to pull upwards on the brick and so prevent it from falling. All materials and structures deflect, although to greatly varying extents, when they are loaded. Figures 4 and 5. It is important to realize that it is perfectly normal for any and every structure to deflect in response to a load. Unless this deflection is too large for the purposes of the structure, it is not in any way a fault but rather an essential characteristic without which no structure would be able to work. The science of elasticity is about the interactions between forces and deflections in materials and structures. Although every kind of solid changes its shape to some extent when a weight or other mechanical force is applied to it, the deflections which occur in practice vary enormously. With a thing like a plant or a piece of rubber, the deflections are often very large and are easily seen, but when we put ordinary loads on hard substances like metal or concrete or bone, the deflections are sometimes very small indeed. Although such movements are often far too small to see with the naked eye, they always exist and are perfectly real, even though we may need special appliances in order to measure them. When you climb the tower of a cathedral, it becomes shorter, as a result of your added weight, by a very, very tiny amount, but it really does become shorter. As a matter of fact, masonry is really more flexible than you might think, as one can see by looking at the 4 principal columns which support the tower of Salisbury Cathedral. They are all quite noticeably bent. Plate 1. Hooke made a further important step in his reasoning which, even nowadays, some people find difficult to follow. He realized that, when any structure deflects under load in the way we have been talking about, the material from which it is made is itself also stretched or contracted, internally, throughout all its parts and in due proportion. Down to a very fine scale as we know nowadays, down to a molecular scale. Thus, when we deform a stick or a steel spring, say by bending it, the atoms and molecules of which the material is made have to move further apart, or else squash closer together, when the material as a whole is stretched or compressed. As we also know nowadays, the chemical bonds which join the atoms to each other, and so hold the solid together, are very strong and stiff indeed. So when the material as a whole is stretched or compressed, this can only be done by stretching of compressing many millions of strong chemical bonds which vigorously resist being deformed, even to a very small extent. Thus these bonds produce the required large forces of reaction. Figure 6. Figure 6. Simplified model of distortion of interatomic bonds under mechanical strain. A. Neutral, relaxed or strain-free position. B. Material strained in tension, atoms further apart, material gets longer. C. Material strained in compression, atoms closer together, material gets shorter. Although Hooke knew nothing in detail about chemical bonds and not very much about atoms and molecules, he understood perfectly well that something of this kind was happening within the fine structure of the material. And he set out to determine what might be the nature of the macroscopic relationship between forces and deflections in solids. He tested a variety of objects made from various materials and having various geometrical forms, such as springs and wires and beams. Having hung a succession of weights upon them and measured the resulting deflections, he showed that the deflection in any given structure was usually proportional to the load. That is to say, a load of 200 pounds would cause twice as much deflection as a load of 100. The word is often associated with rubber bands and underclothes, but it is just as applicable to steel and stone and brick and to biological substances like wood and bone and tendon. It is in this wider sense that engineers generally use it. Incidentally, the ping of the mosquito, for instance, is due to the highly elastic behavior of the resilient springs which operate its wings. However, a certain number of solids and near solids, like putty and plasticine, do not recover completely but remain distorted when the load is taken off. This kind of behavior is called plastic. The word is by no means confined to the materials from which ashtrays are usually made but is also applied to clay and to soft metals. Such plastic substances shade off into things like butter and porridge and treacle. Furthermore, many of the materials which Hooke considered to be elastic turn out to be imperfectly so when tested by more accurate modern methods. However, as a broad generalization, Hooke's observations remain true and still provide the basis of the modern science of elasticity. Nowadays, and with hindsight, the idea that most materials and structures, not only machinery and bridges and buildings but also trees and animals and rocks and mountains and the round world itself, behave very much like springs may seem simple enough. Perhaps blindingly obvious but, from his diary, it is clear that to get thus far cost Hooke great mental effort and many doubts. It is perhaps one of the great intellectual achievements of history. After he had tried out his ideas on Sir Christopher Wren in a series of private arguments, Hooke published his experiments in 1679 in a paper called De Potentia Restitutiva or of a Spring. This paper contained the famous statement ut tensio sic vis, as the extension, so the force. This principle has been known for 300 years as Hooke's law. But to make an enemy of Newton was fatal. For Newton, right or wrong, was implacable. Margaret Espinasse, Robert Hooke, Heinemann, 1956. Although in modern times Hooke's law has been of the very greatest service to engineers, in the form in which Hooke originally propounded it its practical usefulness was rather limited. Hooke was really talking about the deflections of a complete structure, a spring, a bridge, or a tree when a load is applied to it. If we think for one moment, it is obvious that the deflection of a structure is affected both by its size and geometrical shape and also by the sort of material from which it is made. Materials vary very greatly in their intrinsic stiffness. Things like rubber or flesh are easily distorted by small forces which we can apply with our fingers. Other substances such as wood and bone and stone and most metals are very considerably stiffer, and, although no material can be absolutely rigid, a few solids like sapphire and diamond are very stiff indeed. We can make objects of the same size and shape, such as ordinary plumber's washers, out of steel and also out of rubber. It is clear that the steel washer is very much more rigid, in fact about 30,000 times more rigid, than the rubber one. Again, if we make a thin spiral spring and also a thick and massive girder from the same material such as steel, then the spring will naturally be very much more flexible than the girder. We need to be able to separate and to quantify these effects, for in engineering, as in biology, we are wringing the changes of these variables all the time and we need some reliable way of sorting the whole thing out. After such a promising start, it is rather surprising that no scientific way of coping with this difficulty emerged until 120 years after Hooke's death. In fact, throughout the 18th century remarkably little real progress was made in the study of elasticity. The reasons for this lack of progress were no doubt complex, but in general it can be said that while the scientists of the 17th century saw their science as interwoven with the progress of technology, a vision of the purpose of science which was then almost new in history, many of the scientists of the 18th century thought of themselves as philosophers working on a plane which was altogether superior to the sordid problems of manufacturing and commerce. This was, of course, a reversion to the Greek view of science. Hooke's law provided a broad philosophical explanation of some rather commonplace phenomena which was quite adequate for the gentleman philosopher who was not very interested in the technical details. With all this, however, we cannot leave out the personal influence of Newton, 1642–1727, himself, or the after effects of the bitter enmity which existed between Newton and Hooke. Intellectually, Hooke was probably nearly as able as Newton, and he was certainly even more touchy and vain, but in other respects they were men of totally different temperaments and interests. Basically, although they both came from fairly modest backgrounds, Newton was a snob whereas Hooke, though a personal friend of Charles II, was not. Unlike Newton, Hooke was an earthy sort of person who was occupied with an enormous number of very practical problems about elasticity and springs and clocks and buildings and microscopes and Samuel Pepys. Not only was every servant girl fair game to him, but he lived for many years perfect intimie omne with his attractive niece. Newton's vision of the universe may have been wider than Hooke's, but his interest in science was much less practical. In fact, like that of many lesser dons, it could often be described as anti-practical. It is true that Newton became master of the mint and did the job well, but it seems that his acceptance of the post had little to do with any desire to apply science and a lot to do with the fact that this was a place under government which, in those days, conferred a much higher social position than his fellowship of Trinity, not to mention a higher salary. A great deal of Newton's time, however, was spent in a curious world of his own in which he speculated about such perplexing theological problems as the number of the beast. I don't think he had much time or inclination to indulge in the sins of the flesh. In short, Newton was well constituted to detest Hooke as a man and to loathe everything he stood for, down to and including elasticity. It so happened that Newton had the good fortune to live on for 25 years after Hooke died, and he devoted a good deal of this time to denigrating Hooke's memory and the importance of applied science. Since Newton had, by then, an almost godlike position in the scientific world, and since all this tended to reinforce the social and intellectual tendencies of the age, subjects like structures suffered heavily in popularity, even for many years after Newton's death. Thus the situation throughout the 18th century was that, while the manner in which structures worked had been explained in a broad general way by Hooke, his work was not much followed up or exploited. And so the subject remained in such a condition that detailed practical calculations were scarcely possible. So long as this state of affairs continued, the usefulness of theoretical elasticity in engineering was limited. French 18th century engineers were aware of this but regretted it and tried to build structures, which quite often fell down, making use of such theory as was available to them. English engineers, who were also aware of it, were usually indifferent to theory, and they built the structures of the Industrial Revolution by rule of thumb practical methods. These structures probably fell down nearly, but not quite, as often. Asterisk in Hooke's time tension meant what we should call extension, just as tensio did in Latin. Asterisk Hooke's own phrase. Her name was Grace. Or Baron Cauchy in the decipherment of Young's modulus. What would life be without arithmetic, but a scene of horrors? Reverend Sidney Smith, Letter to a Young Lady, July 22, 1835. Apart from Newton and the prejudices of the 18th century, the main reason why the science of elasticity got stuck for so long was that the few scientists who did study it tried to deal with forces and deflections by considering the structure as a whole, as Hooke had done, rather than by analyzing the forces and extensions which could be shown to exist at any given point within the material. All through the 18th century and well into the 19th, very clever men, such as Leonhard Euler, 1707–83, and Thomas Young, 1773–1829, performed what must appear to the modern engineer to be the most incredible intellectual contortions in their attempts to solve what now seem to us to be quite straightforward problems. The concept of the elastic conditions at a specified point inside a material is the concept of stress and strain. These ideas were first put forward in a generalized form by Augustin Cauchy, 1789–1857. In a paper to the French Academy of Sciences in 1822. This paper was perhaps the most important event in the history of elasticity since Hooke. After this, that science showed promise of becoming a practical tool for engineers rather than a happy hunting ground for a few somewhat eccentric philosophers. From his portrait, painted at about this time, Cauchy looks rather a pert young man, but he was undoubtedly an applied mathematician of great ability. When, eventually, English 19th-century engineers bothered to read what Cauchy had said on the subject, they found that, not only were the basic concepts of stress and strain really quite easy to understand, but, once they had been understood, the whole study of structures was much simplified. Nowadays these ideas can be understood by anybody, and it is hard to account for the bewildered and even resentful attitude which is sometimes taken up by laymen when stresses and strains are mentioned. I once had a research student with a nice new degree in zoology who was so upset by the whole idea of stress and strain that she ran away from the university and hid herself. I still do not see why. As it happened, Galileo himself very nearly stumbled upon the idea of stress. In The Two New Sciences, the book he wrote in his old age at Arcatraz, he states very clearly that, other things being equal, a rod which is pulled in tension has a strength which is proportional to its cross-sectional area. Thus, if a rod of 2 square centimeters cross-section breaks at a pull of 1,000 kilograms, then one of 4 square centimeters cross-section will need a pull of 2,000 kilograms force in order to break it, and so on. That it should have taken nearly 200 years to divide the breaking load by the area of the fracture surface, so as to get what we should now call a breaking stress, in this case 500 kilograms per square centimeter, which might be applied to all similar rods made from the same material almost passes belief. Cauchy perceived that this idea of stress can be used, not only to predict when a material will break, but also to describe the state of affairs at any point inside a solid in a much more general kind of way. In other words, the stress in a solid is rather like the pressure in a liquid or a gas. It is a measure of how hard the atoms and molecules which make up the material are being pushed together or pulled apart as a result of external forces. Thus, to say the stress at that point in this piece of steel is 500 kilograms per square centimeter is no more obscure or mysterious than to say the pressure of the air in the tires of my car is 2 kilograms per square centimeter or 28 pounds per square inch. However, although the concepts of pressure and stress are fairly closely comparable, we have to bear in mind that pressure acts in all three directions within a fluid while the stress in a solid is often a directional or one-dimensional affair. Or, at any rate, so we shall consider it for the present. Numerically, the stress in any direction at a given point in a material is simply the force or load which happens to be acting in that direction at the point, divided by the area on which the force acts *. If we call the stress at a certain point S, then where P equals load or force and A is the area over which the force P can be considered as acting. String with a force of 5 kilograms, and the stress in the string will be, or, if we prefer it, 250 kilograms force per square centimeter Oregon kgfcm2. This raises the vexed question of units of stress. Stress can be expressed in any units of force divided by any units of area, and it frequently is. To reduce the amount of confusion we shall stick to the following units in this book. Meganewtons per square meter, mn/m2. This is the SI unit. As most people know, the SI System International habit is to make the unit of force the Newton. 1 to 0 Newton equals 0 to 102 kilograms force equals 0 to 225 pounds force, roughly the weight of one apple. 1 meganewton equals 1 million newtons, which is almost exactly 100 tons force. Pounds, force, per square inch, psi. This is the traditional unit in English-speaking countries, and it is still very widely used by engineers, especially in America. It is also in common use in a great many tables and reference books. Kilograms, force, per square centimeter, kgfcm2, sometimes kgcm2. This is the unit in common use in continental countries, including communist ones. For conversion. Thus the stress in our piece of string, which we found to be 250 kgfcm2, is also equal to 24 to 5 mn/m2 or 3600 p. SI. Since the calculation of stresses is not usually a very accurate business, there is no sense in fussing too much about very exact conversion factors. It is worth repeating that it is important to realize that the stress in a material, like the pressure in a fluid, is a condition which exists at a point and it is not especially associated with any particular cross-sectional area, such as a square inch or a square centimeter or a square meter. Just as stress tells us how hard that is, with how much force the atoms at any point in a solid are being pulled apart, so strain tells us how far they are being pulled apart, that is, by what proportion the bonds between the atoms are stretched. Figure 2. Strain in a bar under tension. Compressive strain is exactly analogous. Thus, if a rod which has an original length L is caused to stretch by an amount L by the action of a force on it, then the strain, or proportionate change of length, in the rod will be E, let us say, such that. To return to our string, if the original length of the string was, say, 2 meters, or 200 centimeters, and the weight of the brick causes it to stretch by 1 centimeter, then the strain in the string is. Engineering strains are usually quite small, and so engineers very often express strains as percentages, which reduces the opportunities for confusion with knots and decimal points. Like stress, strain is not associated with any particular length or cross-section or shape of material. It is also a condition at a point. Again, since we calculate strain by dividing one length by another length i.e. the extension by the original length strain is a ratio, which is to say a number, and it has no units, SI, British, or anything else. All this applies just as much in compression, of course, as it does in tension. As we have said, Hooke's law in its original form, though edifying, was the result of a rather inglorious muddle between the properties of materials and the behavior of structures. This muddle arose mainly from the lack of the concepts of stress and strain, but we also have to bear in mind the difficulties which would have existed in the past in connection with testing materials. Nowadays, when we want to test a material as distinct from a structure, we generally make what is called a test piece from it. The shapes of test pieces may vary a good deal, but usually they have a parallel stem, on which measurements can be made, and are provided with thickened ends by which they can be attached to the testing machine. An ordinary metal test piece often looks like Figure 3. Figure 3. A typical tensile test piece. Testing machines also vary a good deal in size and in design, but basically they are all mechanical devices for applying a measured load in tension or in compression. The stress in the stem of the test piece is obtained merely by dividing the load recorded at each stage on the dial of the machine by the area of its cross-section. The extension of the stem of the test piece under load and therefore the strain in the material is usually measured by means of a sensitive device called an extensometer, which is clamped to 2 points on the stem. With equipment of this kind, it is generally quite easy to measure the stress and the strain which occur within a specimen of a material as we increase the load upon it. The relationship between stress and strain for that material is given by the graph of stress plotted against strain, which we call the stress-strain diagram. This stress-strain diagram, which may look something like Figure 4, is very characteristic of any given material, and its shape is usually unaffected by the size of the test piece which happens to have been used. Figure 4. A typical stress-strain diagram. When we come to plot the stress-strain diagram for metals and for a number of other common solids, we are very apt to find that, at least for moderate stresses, the graph is a straight line. When this is so, we speak of the material as obeying Hooke's law or sometimes of a Hookean material. What we also find, however, is that the slope of the straight part of the graph varies greatly for different materials. Figure 5. It is clear that the slope of the stress-strain diagram measures how readily each material strains elastically under a given stress. In other words, it is a measure of the elastic stiffness or floppiness of a given solid. Figure 5. The slope of the straight part of the stress-strain diagram is characteristic of each different material. E, the Young's modulus of elasticity, represents this slope. For any given material which obeys Hooke's law, the slope of the graph or the ratio of stress to strain will be constant. Thus for any particular material, Young's modulus is sometimes called the elastic modulus and sometimes E, and is quite often spoken of as stiffness in ordinary technical conversation. The word modulus, by the way, is Latin for a little measure. Our string, it may be remembered, was strained 0 to 5% or 0-005 by the weight of the brick, which imposed a stress of 24 to 5 mn/m2 or 3600 psi. The Young's modulus of the string is therefore, since we are dividing a stress by a fraction, which is to say a number, which has no dimensions, Young's modulus has the same dimensions as a stress and is expressed in stress units, that is to say mn/m2, psi or kgf/cm2. Since, however, Young's modulus may be regarded as that stress which would double the length of the material, i.e. the stress at 100% or strain, if the material did not break first. The numbers involved are often large, and some people find them difficult to visualize. The Young's moduli of a number of common biological and engineering materials are given in Table 1. Starting from the cuticle of the pregnant locust, which is low, but not very exceptionally low, for biological materials, the cuticle of the male locust and of the virgin female locust is a lot stiffer. By the way, the Young's moduli are arranged in ascending order all the way to diamond. It will be seen that the range of stiffness varies by about 6 million to 1. Which is a lot. We shall discuss why this should be so in Chapter 8. It may be noticed that a good many common soft biological materials do not occur in this table. This is because their elastic behavior does not obey Hooke's law, even approximately, so that it is really impossible to define a Young's modulus, at any rate in the terms we have been talking about. We shall come back to this sort of elasticity later on. Table 1. Approximate Young's moduli of various solids. Young's modulus, E. Material. psi. mn/m2 soft cuticle of pregnant locust *. 30. Young's modulus is nowadays regarded as a pretty fundamental concept. It thoroughly pervades engineering and materials science and is beginning to invade biology. Yet it took all of the first half. The decipherment of Egyptian hieroglyphics, and who had one of the finest brains of his generation, obviously had a very severe intellectual struggle. Working around the year 1800, he had to approach the problem by a route quite different from that which we have just used, and he considered the question in terms of what we should now call the specific modulus, that is, by how much a column of a material might be expected to shorten under its own weight. Young's own definition of his modulus, published in 1807, is as follows: the modulus of the elasticity of any substance is a column of the same substance, capable of producing a pressure on its base which is to the weight causing a certain degree of compression as the length of the substance is to the diminution of its length. Asterisk. After which, Egyptian hieroglyphics must have appeared simple. It was said of Young by one of his contemporaries that his words were not those in familiar use, and the arrangement of his ideas seldom the same as those he conversed with. He was therefore worse calculated than any man I ever knew for the communication of knowledge. All the same, we have to realize that Young was wrestling with an idea that was scarcely capable of expression without the concepts of stress and strain, which did not come into use until 15 or 20 years later. The modern definition of Young's modulus, E equals stress-strain, was given in 1826, 3 years before Young died, by the French engineer Navier, 1785 to 1836. As the inventor of stress and strain, Cauchy was eventually made a baron by the French government. He seems to have deserved it. It is necessary to avoid confusion between the strength of a structure and the strength of a material. The strength of a structure is simply the load, in pounds force or newtons or kilograms force, which will just break the structure. This figure is known as the breaking load, and it naturally applies only to some individual, specific structure. The strength of a material is the stress, in psi or mn/m2 or kgf/cm2, required to break a piece of the material itself. It will generally be the same for all specimens of any given solid. We are most often concerned with the tensile strength of materials, which is sometimes called the ultimate tensile stress or UTS. This is usually determined by breaking small test pieces in a testing machine. Naturally, the object of many strength calculations is to predict the strength of a structure from the known strength of its material. Table 2: Approximate tensile strengths of various solids. Tensile strength material. PSI. Mn/m2 nonmetals. Muscle tissue, fresh but dead, 15. 01 bladder wall, 34. 02 stomach wall, 62. 04 intestine, 70. 05 artery wall, 240. 17 cartilage, 430. 30 cement and concrete, 600. 41 ordinary brick, 800. 55 fresh skin, 1500. 10 tanned leather, 6000. The tensile strengths of a good many materials are given in Table 2. As with stiffness, it will be seen that the range of strengths in both biological and engineering solids is very wide indeed. For instance, the contrast between the weakness of muscle and the strength of tendon is striking, and this accounts for the very different cross-sections of muscles and their equivalent tendons. Thus the thick and sometimes bulging muscle in our calves transmits its tension to the bone of our heel, so that we can walk and jump, by means of the Achilles or calcaneal tendon, which, although it is pencil-thin, is generally quite adequate for the job. Again, we can see why engineers are unwise to put tensile forces on concrete unless that weak material is sufficiently reinforced with strong steel rods. The strong metals are rather stronger, on the whole, than the strong nonmetals. However, nearly all metals are considerably denser than most biological materials. Steel has a specific gravity of 7 to 8, most zoological tissues about 1 to 1. Thus, strength for weight, metals are not too impressive when compared with plants and animals. We might now sum up what has been said in this chapter. Load. It expresses how or the atoms at a point within a solid are being dragged apart or pushed together. Stress is not the same thing as strain. Strength. By the strength of a material we usually mean that stress which is needed to break it. It expresses how stiff or how floppy a material is. Strength is not the same thing as stiffness. To quote from the New Science of Strong Materials, a biscuit is stiff but weak, steel is stiff and strong, nylon is flexible, low E, and strong, raspberry jelly is flexible, low E, and weak. The two properties together describe a solid about as well as you can reasonably expect two figures to do. In case you should ever have felt any trace of doubt or confusion on these points, it might be of some comfort to know that, not so long ago, I spent a whole evening in Cambridge trying to explain to two scientists of really shattering eminence and worldwide fame the basic difference between stress and strain and strength and stiffness in connection with a very expensive project about which they were proposing to advise the government. I am still uncertain how far I was successful. Except, apparently, the Oxford Dictionary, the words are used, of course, in casual conversation to describe the mental state of people and as if they meant the same thing. In physical science the meanings of the two words are quite clear and distinct. How can a point have an area? Consider the analogy of speed. We express speed as the distance covered in a certain length of time, e.g. miles per hour, although we are concerned usually with the speed at any given infinitely brief moment. Though science is much respected by their lordships and your paper is much esteemed, it is too learned, in short it is not understood. Admiralty letter to Young. Or can you really trust strength calculations?